Good afternoon. Today we are here to discuss about computer organization and architecture. So first thing that we should know that what is computer organization and what is computer architecture. So computer architecture is nothing but the view of computer as presented to a software designer, and computer organization is nothing but the actual implementation of a computer in hardware. Fine. So if you consider this in a layman's concept, then if you think of an example, suppose you are trying to make a building. So computer architecture is nothing but the basic structure of that building, the blueprint of that particular building, and computer organization is how we are constructing the building, that is either by bricks or by using cements or by any other materials. That is the architecture organization of the system. Now first we need to know what is a computer. Computer is nothing but it is a general purpose device that can be programmed to process information and yield meaningful result. So we use often for the purpose of scientific application and other research oriented applications. But it actually how fast it is, why we are using the computers. There are several other devices, but we are using computers instead of other devices. Computers are very fast. So it is our concern that how a computer is so fast, how it became so fast that it can calculate huge numerical calculation into seconds. So the actual speed of a computer is measured into gigahertz. So we know from our 12th standard physics that frequency of a computer is measured in gigahertz, and frequency is nothing but the reciprocal of time period. If we consider frequency, it is nothing but the reciprocal of time period. That is, frequency nu is reciprocal of 1 by tau, time period. So now if the speed of a processor is given as 4 gigahertz, then what is the time period of this machine? The time period is nothing but 1 by 4 gigahertz. That is, if you convert these gigahertz into unit of time, it will become 1 by 4 giga, that is 10 to the power 8, and hertz means 1 by second. That means here we got second. That means 1 by 4 into, if this denominator goes up, then it will become 10 to the power minus 8 second. So it will actually become 0.25 nanoseconds. Fine. That means a computer can execute a complete set of instruction in 0.25 nanosecond if its clock frequency is 4 gigahertz. So it is so fast that within a blink of an eye it can execute a complete instruction. Fine. Now one complete instruction may be of 16 byte, 32 byte or 64 bytes. It depends on the generation of that particular computer. Now how does it actually works? Computer needs some information to process it. So we need some instruction to instruct the computer which will perform some action on the information that are being stored within the computer, and then it will yield meaningful result or the outputs. Now program. What is a program? Program is nothing but list of instruction given to the computer to perform a specific application. So these instructions are previously stored into somewhere of the computer. That means these instructions are provided by the manufacturer or the vendor depending on the generation of the system. The information stored is nothing but the data, the image, the file or the videos that are being stored and on which we want to perform some operation. And computer is nothing but it is a general purpose machine that will process the information and store according to the instruction in the program. So this way it works. You provide some information, you instruct the system to work on that information, and it will work on that information and it will yield some meaningful result. Now if we look into the inside of a computer, then it will almost look like this. So this is the heart or the CPU, and this is the memory or the primary memory we can say, and this is the secondary storage or the hard disk we can say. Fine. Now the primary memory is said to know as the onboard memory, as it is attached with the motherboard for the CPU, and the hard disk is called secondary storage or the off-board memory, as it is connected through some connecting medium to the motherboard, that is serial ATA or parallel ATA. If we go through the memory systems of a computer, we can see lots of memory devices are there within the computer. Fine. If we write them down, then first comes the CPU registers. That means the registers which reside inside the CPU. There are several types of CPU registers, that is the accumulator, the program counter, the instruction register, MAR or memory address register, MBR or memory buffer register, and n number of general purpose registers. So actually these are called the special purpose registers or the SPR. That means these registers are specifically used for some particular purpose, and these registers are called the general purpose registers. So there are n number of general purpose registers and some special purpose registers. Special purpose registers, that is the accumulator, is basically the processor registers. That means processor use this accumulator to perform operation and to store intermediate values. Suppose we want to add 3 numbers. Now we first add 2 numbers, and then with the intermediate result or the added value we add the next number. So we have to store the intermediate value. That intermediate value will be stored within the accumulator. Program counter is nothing but a special register that is keep tracks of the last instruction to be executed. The instruction register is nothing but another register which keep track of the instruction next to be executed. Another register is there, that is the stack pointer. Stack pointer keep tracks on the last memory address, the top of the stack. If we need some interrupt within our program, then we need to store the entire program into a stack and provide some interrupt service to the interrupt occurred. And for that particular purpose, we need the stack pointer, so that we are pushing the value into the stack. We can restore the value from the stack when the interrupt service routine is completed. So we need stack pointer to locate the last memory address from where the program has been paused, and it is the back address or the return location of that particular program. MAR is the memory address register and MBR is the memory buffer registers. So these are the CPU registers. After CPU register, there are cache memory. These are also used to store information in a particular manner. After that, there are primary memories, then secondary, then tape and disk unit. So we can find out several memory devices within a computer system. So these devices are of different category and of different speed. So if we use, what will happen if we use one particular kind of memory? The computer will become so much costly. If we use these type of memory only, and the computer won't be so costly if we use this type of memory, but in that case the computer will lag due to low speed. So this is a memory hierarchy, and if we go through the memory hierarchy, if we look up, then we can see the speed is increasing, the cost per byte is increasing, but the size is decreasing. The size is higher if we use this sort of devices. These have higher size, and if we move upward, the size will decrease. So to make a computer economic and general purpose, we use all these sort of memory together, so it can be used by everyone. Now, how it looks like? So there will be memory or the primary memory that we have discussed, and the secondary storage or the hard disk along with the CPU. Now, memory, it actually stores programs, data, and it gets destroyed when the computer is off, that is power is down, where it actually happens in the primary storage or the RAM. Right? And the hard disk is nothing but a magnetic disk unit that stores program or data permanently. That means when we power off the system, no data will get removed or get destroyed. It will hold the data for the time. Now, if we make it a full system, then it will more look like that. The CPU, the primary memory, the secondary storage, and the I/O devices, that is the keyboard and the mouse, and monitor and printer. So this is our full system. This is how it works. Now, how does an electronic device differ from our brain? So it is very fast. We see that the computer is very fast. So there are some features of computer. What are the features? These are the features are, if we consider computer and our brain together. So in case of intelligence, the computer is dumb and our brain is intelligent. That means if we provide some instruction to a computer to perform a particular task, it can perform the task. But if it is unknown to a computer system, that means the instruction that we are giving is not given inside the computer, then it will not able to perform that particular task. But if we provide a particular task to a human being, then if a thing is unknown, then by calculating or by using the brain, we can solve the particular problem, thus became intelligent. So computer is not intelligent. We make them intelligent by putting some features. Now, speed of basic calculation. In case of computer, the speed of basic calculation is ultra fast or very fast. But in case of our brain, it is slow. Notice directly we cannot say that our brain is slow, but if we put enormous calculations, that means a calculation with huge number of data, then it will become slow. Now our brain get tired after some time, but as computer as an electronic device, it will never get tired and it will never get bored. So it is an ultra fast and ultra dumb device together. So we need to make it intelligent. Computer is not at all intelligent. We provide the instruction inside the system, and according to that instruction the computer works. Fine. So if the computer doesn't have that particular instruction, that how to process the particular data or how to process the particular information, the computer cannot work accordingly. So how to instruct a computer? So basically we instruct a computer by means of programs. So what are programs? Programs are nothing but set of instructions that are written in a high level language. Basically you have heard that C, C++, Java, ASP.NET, these are high level languages through which we can write programs. Now after writing the program, we need to compile the program. Compiling means checking for errors and other mistakes if there is any. Fine. So compile that program into a format that computer actually understands, because the program which we have written in a high level language, computer doesn't understand that particular program. So we need to convert that particular program or that set of instruction into a computer understandable one. So we need to compile that particular program into an executable program, and after compilation the executable program executes and provides some particular output. Fine. So what can a computer understand? From the previous slide we knew that a computer doesn't understand the high level language. So computer clearly cannot understand the instruction that we basically use in our general life. That is, if you want to multiply two matrices, so you say the computer that I want to multiply two matrices, or compute the determinant of a matrix, or find the shortest path between Mumbai and Delhi. So computer cannot understand this sort of language. So there are specifically some set of language or some set of rules that are being understood by the computer. So if you write A plus B, it will be understood by the computer. If you write like this, C equals to A plus B, then the computer could understood. Fine. Or if you write C A star B, then computer could understood that we want to multiply A with B to get C. So these are actually operator and operands. So in an instruction can be typically divided into two segments. That is, if we consider these as an instruction, then these are the operators on which we are working, and these are the operands with which we are working. So these operators are provided by the users. Within the program, these operators are provided by the user, and operands that are being used by the users, here this is an addition operator, this is an assignment operator. So these sort of operators are already pre-provided within the system so that the system could understand. So the language of instruction, human can understand the language. Now it is complicated sentence like English, French, Spanish, fine. So human can understand those, but computer, they cannot understand this sort of language. So they understand only very simple instruction. So if you consider that computer only understands binary values, so binary values are actually machine level language. If you level up a bit more, then you can find assembly language, that is basically understood by the computer, that is machine understandable code. So all these language have some operator, some operands and some other features, and if we put those together, then it will become a language with some specific set of rules that what we can do and why we cannot do. These things, or this sort of what you can say, that this sort of a language can be very well defined and very carefully covered with semantics, that are the restrictions that can be done or that cannot be done. So what are the do's and what are the don'ts? These are the semantics. Fine. That is, if you pronounce a particular thing in your language, that is CAR, so it becomes car. Fine. But if you write like this, it signifies nothing. So there are some set of rules that which can go after what and how to put them together. These rules are called the semantics. So the semantics of all the instructions that are supported by a processor or by a microprocessor is known by its instruction set architecture. So this also includes the semantics of the instruction themselves, along with the operands and the interfaces with the peripheral devices. So the actual feature of the instruction set architecture is nothing but the example of instruction in an architecture. That is the arithmetic instruction. That is, if we try to perform subtraction, addition, multiplication, division, these sort of operations. The logical instruction, that means the logical and, logical or the logical not. And residual are the nothing but data transfer or data movement instruction. That means if we want to move data from one location to another, then we need the data transfer or data movement instruction. This is one of the feature of the instruction set architecture. The next feature of it, this should be complete, that it should be able to implement all the programs that user may write. So if we provide a particular semantics to the user, that how they can use or how they can write in that particular programming language environment, then it should be able to implement all the programs that are being written by the users. Next is the conciseness of the instruction set architecture. That is, the instruction set should have a limited size. That means you cannot provide huge size of instructions. That is, an instruction set architecture contains 32 to at most 1000 instructions. So if we put more instruction, then it will become tedious to look up for that instruction and work according to it, fine, within a limited time span. Now the next feature is genericity. That is, instruction should not be too specialized. That is, add 14. So if we say add 14, it will understand that you want to add 14 with something. Now here this add a number with 14. This number is not specified here. So it is a specialized instruction that says add 14 with another number. Which number? That I am not mentioning. So these sort of specialized instructions are avoided. So instruction should not be too specialized, that should be generic. And the last but not the least is simplicity. That is, should not be very complicated, it should be very, very simple so that it can be understood by the system. Now, after completing all these features, if we try to design an instruction set architecture, the important thing that we need to be answered or that we need to thought at how many instructions should we have and how should they do and how complicated should they be. So these are the questions that will arise. So if we want to design different sort of instruction set architecture, then there will be two type of instruction set architecture. One is reduced instruction set computer, another is complex instruction set computer. There are two different paradigms used in different computer system. In complex instruction set architecture, there are short number of instructions, but instruction length is too much high. And in case of reduced instruction set computer, there are instructions are very short and there are too many instructions. So we'll discuss it in a precise way on our next class. So the summary that we have learned up to now is computers are dumb and yet they are very fast machines, and they use instructions which are basic redundant commands used to communicate with a processor. That is, a computer can execute billions of instructions per second, that we have seen from the calculation of our first slide. The computer transforms a user program into a high level language to a machine understandable code or basic machine instruction. The instruction set architecture that refers to the semantics of all the instructions supported by a processor. And last but not the least, the instruction set that needs to be complete, and it is desirable if it is also concise, generic and simple. So that's it, the content for today's class. That's it. We'll continue with our next session very soon. Thank you.